Welcome, friends, to Unit 11 on trigonometry. As a reminder, as with any video, make sure that you use the power of pause, stop, and rewind. I'm going to go through the lesson so that we make the video as short as possible, so feel free to stop and rewind when necessary. All right, so this is just an outline of what to expect. We have 7 lessons, so it's a pretty meaty, pretty long unit. Highlights include, after the first 3 lessons, you're going to have a quiz, and then your Unit 11 exam. So I highly recommend that as we go through the lessons, do your homework for Lesson 1 after this video. When we do Lesson 2, I want to make sure that you are reviewing Lesson 1. When you do the homework for Lesson 3, make sure that you're going back to the previous lessons and that you're constantly taking that 5 to 10 minutes on your off days when we don't meet to review. I think that will go a long way. All right, so on Lesson 1, we're going to talk about angles and their measures. And by the end of this lesson, you should know how degree and radian measures are related and how we are using them to model and solve real-life problems. So this lesson consists of 5 mini lessons, A through E. So if it were me, I might watch the first part of this, and then there is an assignment that is given, and it's up to you if you want to stop and do the assignment or do the assignment in class the next day and take notes. But just know that I've kind of have taken this lesson and divided it into 3 parts. All right, so here's the first part. You need to understand what it means to put an angle in standard position. I can draw any angle in white space. Okay, I can draw any angle I want. But once I draw that angle on an XY coordinate plane, so an XY coordinate plane, I have now put an angle in standard position. Whenever you put an angle in standard position, we are always going to put the initial side, the first part of the angle. It is always going to be written on the positive x-axis. Then the terminal side, and think about terminal. Terminal is where something ends. Where it ends can be someplace lying in the quadrant. So in this example, I have it lying in the second quadrant. As a reminder, here's your first quadrant, your second quadrant, your third quadrant, and your fourth quadrant. Okay. The vertex is always located at the origin. And this is what makes something in an angle in standard position. You must have the arrow. You must have the direction. So by writing this arrow, this tells me that I am looking at this angle and I am going in a counterclockwise rotation. All right. If I was looking at this angle, the arrow would have, that I have highlighted in green, the arrow would have been going in that direction. So direction is important. As I get rid of the green, when we talk about an angle in standard position, it's not just this ray, it's not just this ray. You also have to denote a direction. So that entire angle is considered in standard position, and therefore we can measure these particular angles. If I would draw an initial side and I would draw a terminal side, both on the positive x-axis, then that would be an angle that has 0 degrees. If I drew an initial side on the positive x-axis and the terminal side on the positive y-axis, that would be an angle that's 90 degrees. If I would draw an angle where the initial side is on my positive x-axis and my terminal side is on the negative x, then my angle would be 180 degrees. If I drew my initial side and then my terminal side was on the negative y-axis, then that would be 270. And then one complete rotation, if I go all the way around, is going to be 360 degrees. So let's practice. Let's draw some angles in standard position. I'm not going to be the graph police. I'm not going to put up my protractor and make sure you're exactly at 210. Here's what I'm concerned with. All of you should start at the origin, and before I even look at the problem, I have my initial side. On a 210 degree angle, I'm looking for that you have the terminal side in the correct quadrant and that you have your arrow in the right direction. So if I went 210 degrees, well, clearly I am going to be more than 90. Okay, I'm going to be more than 180, but I am going to be less than 270. So it's going to put this in the third quadrant. So again, I'm just going to draw my terminal side in the third quadrant. Remember, from the initial side to here is 90. This is 180. So then this would give me a 210 degree angle in standard position. That's all I need. All right, a negative 45 degrees. When you can have negative angles. When you have a negative angle, this talks about direction. So a negative 45 degree angle is still going to start at the origin with an initial side on the positive x-axis. But instead of going in a counterclockwise direction, like I did in the previous problem, with the 210 degrees, I went counterclockwise. Okay, with a negative, you're going to go clockwise. Okay, so a positive 45 degree angle would be located in the first quadrant, but this is a negative 45 degrees. So if I go this direction, this is negative 90 degrees, this is negative 180 degrees, this is negative 270, back to negative 360. So if I want to go a negative 45 degrees, I am going to go halfway through the fourth quadrant, and this would be my negative 45 degree angle. Let's look at C, 510. Here's the issue with 510. I'm still going to start at the origin. I'm still going to draw my initial side. But if I go one complete revolution, that's 360 degrees. I still haven't gotten to 510. So I can take 510. We're going to subtract 360. All right. So that's going to give me 0, 5, 150. So I have to go 150 extra degrees. So this is going to give me to extra 90. I don't need to go to 180. So my terminal side is going to fall in the second quadrant. Now, I know this looks like a big loop-de-loop, but it is imperative that for my final answer to be correct, I do need that loop-de-loop-de-loop. Because if all you wrote was from here to here, this is 150. I needed that extra revolution in order for myself to get to 510 degrees. So what I have listed in red, and I will highlight in yellow, is my final answer as an angle in standard position. 510 and 150 have an interesting relationship. They are considered coterminal, and they are coterminal because even if I would graph a 150 degree angle, the initial side and the terminal side would be the same. Their terminal sides coincide. Coincide means the same. Now they are not the same angle. 150 goes from the initial side to that angle in the second quadrant immediately. 510 has another revolution, but that makes them coterminal. If I would make it 2 revolutions to get there, that's coterminal. If I would make it 3 revolutions to get there, that's going to be coterminal. The revolutions are what makes them coterminal angles. Again, they are not the same angle, they are coterminal. So the numeric relationship between these two measures is going to be 360 degrees. 150 plus 360 gives me 510. So 150 and 510 are considered coterminal angles. Now, let me redraw this relationship. So again, I can have 510, okay, or I can have 150, but those were both positive angles. I can also be coterminal with this angle by going in a negative direction. So I could go this way. So I could take 3, or I guess technically we would be taking 150 minus 360. I could be going in a negative direction, and that is going to give me, so if I take 360 and I subtract 150, that gives me 210. So a negative 210 degree angle is also coterminal with 150 degrees, 510 degrees, negative 210. If I wanted to continue getting more coterminal angles, I could keep, so here, so if I take 150 and subtract 360, okay, I can keep subtracting 360. Negative 570 is coterminal. Negative 930 degrees is coterminal. Negative 1,290 degrees is coterminal. So I think hopefully you're catching my drift. I can also keep adding 360. If I take a 150 degree angle and add 360, I get 510. That is coterminal. If I add another 360, 870 is coterminal. If I add another 360, 1,230 is coterminal. All of those angles have initial sides and the terminal side at the same place. The difference is the number of revolutions it takes to get there. So when you are asked problems like the following, where you have one positive and one negative angle that is coterminal with the given angle, all you basically have to do is, in order to get the positive, you have to keep adding 360 until you get a positive. And in order to get a negative coterminal angle, you keep subtracting 360 until you get a positive or coterminal angle. So just for the sake of organization, I'm going to do a lot of this work on my calculator so that it's clear. If I have a negative 60 angle, I can add 360 to it, and 300 is a positive coterminal angle. It is not the only answer. If you wanted to be wild and crazy and add another 360, 660 is also an answer. If you wanted to add 360 again, 1020 is also a positive coterminal angle. Do you need to give me all three? No. In my opinion, I would add 360 the first time, write down 300 and move on with my life. But please know that any of those, there's infinite amount of answers. When I want to find a negative coterminal angle, I'm going to subtract the negative 60 degrees, and now I'm going to subtract 360. So negative 420 can be an answer. Negative 780 could be an answer. Negative 1140 could be an answer. Again, none of those are, you don't have to give me all of them. I would have given probably this answer, negative 420, and then moved on with my life. But again, I want you to understand that you can have multiple answers. All right, 495 degrees is, we want a positive and a negative coterminal angle. So kind of similar, all right? If I take 495, I can add 360 to get a positive coterminal angle. I could add another 360. Those are both considered positive coterminal angles. But watch kind of what happens when I go for the negative. If I take 495 and I subtract 360, I still get a positive answer. So I can't use 135 as the answer to a coterminal angle that's negative. You need to keep adding 360 until you get a negative. So in this problem, the most common answers that kids will give me, a lot of them will just add 360 once to get a positive. Or some of them notice if you subtract the revolution, you get 135. Please understand that all of those are correct answers. The ones circled are the most common that I'll get from students. And the most common answer I would get from students in terms of my negative coterminal angle would be negative 225 degrees. Okay. All right. What is the complement and supplement to 142 degrees, 32 minutes, 40 seconds? I spoke with Ms. Judd, and she said that you went over this briefly last year. But here's the idea. A degree is very, very small. If you think of a protractor and how this is 1 degree, 2 degrees, all the way to 90 degrees, this is considered a minute. This is considered a second. A minute is 1/60th of a degree. In other words, you need 60 minutes in order to make 1 degree. It works very much like time. And a second is 1/60th of a minute. So it takes 60 seconds in order to equal 1 minute. They are parts. You might not think that it's really important to be talking about that small of a quantity. I mean, think about 1 degree. 1 degree is so hard for me to draw up on the board. And now we're going to split that up into 60 pieces and split each of those into 60 pieces. But a lot of times degrees, minutes, and seconds is definitely used in the nautical world. And when you're on a map and you're trying to get from point here to point here, and this is like a big city with multiple ports, when degrees and minutes, when you're in the ocean and you've got open water, your trajectory of a degrees, minutes, and seconds, or in your longitude and your latitude, can definitely make a difference. Please don't be scared. This is something that you can do on your calculator, and I'm going to wait till you're all in class working on this to show you those instead of taking up video time. But to do it by hand, when we talk about the complement, these are 2 angles whose sum equals 90 degrees, and a supplement are 2 angles whose sum equals 180 degrees. So I need to find an angle, I was right, plus 142 degrees, 32 minutes, minutes, 40 seconds, that equals 180. So basically you need to subtract that, and no, you don't have to write all this out. I'm just trying to make it clear. All right, so if you're going to do this by hand, then you're going to have to use some borrowing. Okay, 180 can be written as 179 degrees, 59 minutes, 60 seconds. Okay, because 60 seconds is 1 minute. If I add 1 minute to 59 minutes, I get 60 minutes, and 60 minutes is 1 degree, which would give me 180 degrees. And folks, this is pretty easy to do. 60 minus 40 is 20 seconds. 59 minus 32 is 27 minutes. And 179 degrees minus 142, what's that going to give me? 7, 3. So 37 degrees, 27 minutes, 20 seconds. This would be the supplement of 142 degrees, 32 minutes, 40 seconds. Now let's talk about the complement. All right. We would do the exact same thing. We would take 90 degrees and we're going to subtract 140 degrees, 32 minutes, 40 seconds. But oops, this exceeds 90. And the definition of a complement are two angles, exactly two angles, that their sum equals 90. So 142 degrees, 32 minutes, 40 seconds does not have a complement. There is no complement. Okay? Just for your knowledge, if there was one, like if I wanted you to find the complement of 52 degrees, 40 minutes, 29 seconds, if I wanted you to do that, then we would take that away from 90, okay? And we can rewrite 90, the power of a raise, as 89 degrees, 59 minutes, 60 seconds, and I would subtract. So this is going to give me 31 seconds. This is going to give me 19 minutes, and this is going to give me 38 degrees. So this would be the complement of an angle that is 52 degrees, 40 minutes, 29 seconds. All right, so this is the first learning opportunity. You can try page 456, numbers 1 to 25 odd at this time. All right, radian measure. So far, the only way you have measured angles is by degrees. And if you go to Home Depot and you are trying to order a window dressing for like a Norman window, maybe some of you have windows that look like this in your house, you can go tell them that you have a 180-degree window. Okay, I have a window that is 180 degrees, and they're going to look at you funny because 180 degrees is not going to tell them specifically how much blinds you need or how much window dressing or how much or what the length is of that 180-degree angle. This is the purpose of radians. Degrees, in my opinion, measures up an opening. That's what degrees does for me. What radian measure does is it gives me a length. So yes, I know that this arc is 180 degrees. It's a half a circle. But how specific, how long is it? It's obviously half the circumference of a circle. And so I can do that much, but I need some more information. I'm going to need the radius, because without the radius, I'm not going to be able to compute the circumference to take half of it. So you're going to notice that radian measure is definitely related to the circumference of any circle. So this is the big idea of radian measure. I think sometimes you know how to compute it and you don't know what it means. Radian measure has to do with length. So with that said, the definition of a radian is the following. 1 radian is the measure of an angle in standard position let me not make that 90. Okay. All right, whose terminal side intercepts an arc. So if I would make this into a circle, here's my arc. And this length is the same as this length, is the same as this length. That's what a radian measure is. And I think that that's very abstract. And so if you wanted to take a bunch of circles and measure off their radius, cut arc that is the same radius, you will notice that the following is going to happen. Okay? I have, hopefully this will be a graphic for you that is helpful. This is an arbitrary or random circle, and I have highlighted the radius. So this radius, this red, is going to represent the R that I had before. Okay, that's my radius. All right. All right. So now, when I move that radius, this is a length right here. That is 1 radian measure along the circle. This is the second radian measure. It's the radius length on the arc of the circle. This is my third radian measure. This is my fourth radian measure. Here is my fifth radian measure. And here is my sixth radian measure. And I'm hoping that the following makes sense. Do you see how you've got a little bit left over? Well, think about this as a half a circle. Didn't we had one, it stopped about there, this stopped about here, this stopped about here. This is 1 radian, here's 2 radians, here's 3 radians with a little bit more. Here was my 4th radian, here was my 5th radian, here was my 6th radian with this little extra. Well, isn't this 180 degrees? Hello? 1, 2, 3, and a little bit over, that's pi. So 180 degrees is equivalent to pi radians, no matter how big or how small the circle is. This would be another pi. So in radian measure, 360 degrees is equivalent to 2 pi in terms of radians. Again, feel free to stop and rewind and think. So, isn't 360 degrees equivalent to the entire circumference of a circle? All right, the equation for the circumference of a circle, or the expression, is 2 pi times the radius. All right, we are going to be heading towards unit circle. So I'm not saying that every circle has a measure of 6.14, but it all has that same ratio, 6.28, 2 pi. But all you would have to do is take that 2 pi and multiply it by whatever radius you are dealing with. So when we talk about our radian measures, we refer to the unit circle where we set the radius equal to 1. Therefore, 360 is equivalent to 2 pi radians. That is a length. It is a length of approximately 6.28 units. All right. So what is 180 degrees in radians? Well, if we know that we have 360 degrees is equivalent to 2 pi radians, and then that means half of 360 is 180, so half of 2 pi is pi, so 180 degree in radians would be pi. 90 is half of 180, so half of pi would be pi over 2. 45 is half of 90. So half of pi over 2, of means multiply, would be pi when I multiply the tops together over 4. The problem is if I asked you what is the radian measure of something like 37 degrees, what the heck are you going to do? You can't keep taking half and a half and a half. So I'm letting you know that if you look in the book will tell you to take something and multiply by pi over 180 or 180 over pi. Maybe that's what you remember from last year. It is not wrong. This is okay. What I find is that students forget when they're supposed to multiply by pi over 180 or 180 over pi. So I teach the general way to convert from radians to degrees via a proportion. It never fails. It works every time. How did I get it? Well, a proportion is just a ratio. So I can compare radians to degrees. And didn't we determine that the radian measure of 2 pi is equivalent to 360 degrees? And all I did is reduce the 2 over 360 to get the 1 over 180. It's just a simple proportion. So as we're going to convert between radians and degrees, if I want to convert 110 degrees to radians, I say to myself, I have radians over degrees equals pi over 180. Okay, I'm going to use the power of erase. They gave me a degree, so I'm going to put in 110. Now, I want your answer to stay in terms of pi. That means I don't want you to multiply by 3.14. I do not want decimals. I want your answer to have pi in it as a final answer. So if I cross multiply, I have the radian measure times 180 is equal to 110 times pi. I'm going to divide by 180. So the radian measure equivalent to 110 degrees is 11 pi over 18. And you can use technology to reduce that. On your TI Inspires, you just type it in. On the 84s, if I take 110 and I divide it by 180, okay, and I math bracket, it gives me 11/18. Okay. All right, now for part B, let's convert negative pi over 9 radians to degrees. Again, I start out. Radians to degrees is equal to pi over 180. And if you don't remember the pi over 180, then make it 2 pi over 360. Okay, in this case, they gave me the radian, so I'm going to fill in negative pi over 9, and I'm going to cross multiply. This looks like it's going to be ugly, but have some faith in me, it's going to be okay. Degrees times pi is going to equal to pi over 9 times 180, right? I might write out more steps than you need, but degrees times pi is equal to negative 180 pi over 9, because I just multiply the tops together and the bottoms together. And then negative 180 divided by 9 is going to give you negative 20 pi. Divide both sides by pi. So the degree measure is negative 20. Notice how the negative does not go away, because if you're starting with a negative angle to begin with, all it's denoting is a different direction. So we have not changed the direction when we convert to radians degrees. What we did is we talked about the length. So just use your brain for just a minute. 110 degrees in standard position, all right, is going to be a second quadrant angle. And if you remember what I just showed you, where this was 1 radian in the time before this, here's a radian, here's a radian, here was a radian, here was a radian, here was a radian. Doesn't it look like 110 is in this vicinity between 2 and 3 radians? And if on my calculator I do evaluate using pi, all right, so if I do take 11 times 3.14 and then divide that by 18, do you notice how I get 1.19 as a decimal? This is a radian measure. So if I go 1 radian and then 1.9 of a radian, that is where 110 degrees fell. If this is a circle with a radius of 1, then this length from here to here would be 1.91 units. If it is a circle that is not having a radius of 1, let's say the radius was 4, all I would do is take the 1.91 ratio and I would multiply it by 4 to get that length. If the radius of a circle was 10, then I would multiply it by 10. That's how radians work. Similarly over here, I'm just trying to get you to think about this. All right, you can do the homework problem, guys. I showed you how to do it, but think about it. A negative 20 degree angle is going to be here in the 4th quadrant. Negative pi over 9 radians. Okay, let me show you what that means. Okay, so 3.14 divided by 9. Okay, that is negative 0.34 radians in terms of a decimal. So hopefully this makes sense. If I'm going in a counterclockwise direction using that animation I did before, this was 1 radian, 2 radians, 3 radians, 4 radians, 5 radians, 6 with a little bit left over. We're saying that a negative 20 degree angle is only about 0.34 or a third of 1 radian. And that should hopefully kind of make sense. All right, so let's put this whole lesson together. You need to be able to draw an angle in degrees or radians in standard position, find positive and negative coterminal angles given an angle in either degree or radian measure, and convert between the two. So for instance, draw an angle with the given measures in standard position and find 1 positive and 1 negative coterminal angle. You need to work with me here on the fractions, friends. It is perfectly acceptable to convert to degrees, do it all in degrees, and then to radians. I feel like you're doing yourself a huge disservice. You need to start thinking in radians. We're learning the algebra of calculus, and we very rarely, if ever, do calculus with degrees because you can't work with it. You have to work with distances. So with that said, when we want to try to draw this angle in standard position, all right, this is 0 degrees, 0 radians. All right, this is 90 degrees. This is 180 degrees, this is 270 degrees, and we're back to 360. And I know that you feel comfortable with your degrees. Let's break this down in radians. 360 degrees is 2 pi radians. Half of 360 is 180, so this is pi radians. Half of 180 is 90, so this has to be pi over 2 radians. And 270 is the one that's kind of the kicker. I'm going to let you on your own convert it, but think about this. Isn't this from here to here a half a pi? All right, here to here is a whole pi, so another pi over 2, right? Distance, this is another pi over 2. 1, 2, 3. This gives you 3 pi over 2. And then I get back to 4 pi over 2, which gives you your 2 pi. So you can think of each of these quadrants as a distance of pi over 2. So knowing this, if I have 7 pi over 4, isn't 7 pi over 4 as a mixed fraction 1 3/4 pi? Okay, so when I go to graph this in standard position, all right, here is my terminal side, initial side. My terminal side has to be 1 3/4 pi. So here is a half pi, here is a whole pi, here is 1 1/2 pies, so another 3/4 is going to put me in the fourth quadrant because 1 3/4 doesn't get me quite to 2. So 7 pi over 4, this is its angle in standard position. Okay. Now let's talk about getting one positive and one negative coterminal angle. You remember that we got positive and negative coterminal angles by adding 360 and subtracting 360. So in radians, this means we have to add 2 pi or subtract 2 pi. So let's do some work. It is fraction work, and your refusal to embrace the fractions will be your refusal to be successful in future courses. This is not bad. I'm not asking you to find coterminal angles of 5 pi over 362. It's 7 pi over 4. So when I add 2 pi to this, I have to get a common denominator. So 7 pi over 4 is equivalent to 8 pi over 4. Converting 2 pi into something is not very difficult. So when I add these together, I get 15 pi over 4. Now, to find a negative coterminal angle, I subtract 2 pi, which we've already converted to fourths as 8 pi over 4, so I get negative pi over 4. Here's my positive coterminal angle. This is my negative coterminal angle. And I'm going to go out my business. Okay. All right. Negative 3 pi over 2. So here is my initial side. Now, this tells me I have to go in a negative direction. So this is a distance of negative pi over 2. This is going to be a distance of another negative pi over 2, so negative pi. Here is another negative pi over 2, so this is a negative 3 pi over 2. So this is the angle negative 3 pi over 2. Okay. And I need to get one positive and one coterminal angle. So I'm going to take negative 3 pi over 2, and I'm going to add 2 pi. 2 pi in terms of halves is going to be 4 pi over 2. And when I add them together, I get pi over 2. Now I'm going to get another negative coterminal angle, which is negative 7 pi over 2. Let's do C, 7 pi over 8. Remember the power of pause and stop. Okay? So 7 pi over 8. I want to do 7/8 of a pi. 7/8 of a pi. Well, if I go to here, this is a half a pi, right? And if I go out here, this is a whole pi. So 7/8 is falling between a half and a whole. So it's going to be somewhere over here. In fact, I would argue 7/8 is pretty close to 8/8. 8/8 would be 1. So this is 7 pi over 8. And if we want to get my coterminal angles, I'm going to take 7 pi over 8, and I'm going to add 2 pi, which would be 16 pi over 8. So 23 pi over 8 would be a positive coterminal angle. And then if I subtract that, I'm going to get negative 9 pi over 8 as another negative coterminal angle. So now you can attempt page 457, 25 to 67 on. And last but not least, these are pretty kill and drill, guys. These are 2 formulas you need to know. Being able to find the arc length. Arc length is being able to find the length of a circle. And this is when we're going to do a circle where we don't have a radius of 1. And then here is your area formula. The issue here is in order to do this, if we are talking about length, and we are talking about area, you cannot input degrees. Degrees does not define length. Your theta must be a radian measure. So other than a couple of formulas, the only tricky part to this is you need to make sure that you convert any degrees into radians. Again, this is something from geometry. So if you want to find the arc length and area of a sector with a radius of 9 centimeters and a central angle of 60 degrees, for those of you that need to see the picture, we're talking about a circle, all right? And we have a radius of 9, and we have a central angle that is 60 degrees. The question is asking for find the area or find the arc length. So when I want to find the arc length, which is denoted as S is equal to R times theta, my radius is 9, but I cannot put 60 degrees in there. 60 degrees is not a length. Remember, the arc length, and just to review, the central angle and the length of the arc are the same. So the arc length is also 60 degrees. So radians over degrees equals pi over 180. All right, they gave me that my degrees was 60. I'm going to cross multiply. So I have 60 pi is equal to the radians times 180. I'm going to divide by 180. I don't need a calculator because I'm keeping my answer in terms of pi. So the zeros cancel, and then 6 over 18 reduces to 1/3. So my radian measure is pi over 3. Okay, so my arc length in terms of pi is 9 pi over 3, which is 3 pi. Okay, and for those of you that need a little bit more concrete, if I take 3 times 3.14, that means that arc length is approximately 9.42 units. Okay. Now we're going to find the area of the sector, which again, we are just going to use this area formula. Okay. So the area formula is equal to 1/2 r squared times theta. So my radius is 9, and we've already determined that theta is pi over 3 radians. All I have to do is multiply the top numbers together, multiply the bottom numbers together. So I get 81 pi over 6. All right. And if I take 81 divided by 6 and I math bracket, that gives me 27 over 2. So my final answer is 27 pi over 2 units squared. All right, so your final learning opportunity is page 458, number 69 to 79 odd, 81, 85, and 89. And please see me in class and look at your text for help with the application problems. Thanks for listening.